Okay, so earlier in the chapter, we calculate the force on a dipole by brute force, so to speak, but there is another method, as you may have concluded from most of the theory. There's more than one way to get to the same result. And the book supposes that the more elegant approach to this is to write the magnetic field as a Taylor expansion about the center of the loop, and then apply everything we know to find the force. So if we do that, we approximate BR is equal to BR naught plus the difference in the separation vectors times the gradient at the field, or the del operator at the origin point, times or distributed to the B at R naught, where R naught is the position of the dipole and del naught denotes the differentiation with respect to R naught. Okay, so if we put this into the Lorentz force law, we get this integral here. And we just have a whole ton of little messiness to deal with within the cross product here. And what this tells us is that with the cross product, we know we have signs in various directions that change, which is confined within this epsilon symbol, epsilon ijk. That's the Levi-Civita symbol, and I'll talk more about what that means later. But basically, we're moving this through in order to automate the process of how to compactly find these curls and cross products within this definition. But what we'll need to note here is that these symbols eventually add up to the Dirac delta or the Kronecker delta that we've dealt with previously in Chapter 1. And that should make sense because if I have two things running in the same direction, then their cross product is 0. And that's what these two things are trying to tell you. These symbols are something that we see throughout the landscape of physics, so it's best to get your hands, wet and dirty and, figure out how to use these things. You're going to see them again, especially in quantum mechanics. They're everywhere in the field theory, so best be prepared. All right, so if we're looking at how to play with this stuff, let's start back from the force equation. And then we see here that if we tidy up this thing after we plug in the expansion, we have the line integral crossed with the initial field, and then we also have I times the integral across the separation part of the field, minus after we distribute, because remember it was R minus R naught, and we still get the same thing, but now we have to confine everything down. We see, however, that the only part that we have is with respect to the origin, because everything else will cancel out due to the closed loop equaling 0. And it's going to be very powerful because of where the loop was defined with respect to the origin. Now we just have to focus our attention here. And what that tells us is that the dl cross b naught, I being some indice, is equal to the Levi symbol with respect to every differential element and their corresponding B component. And similarly for this dot product, we have the dot with the del operator, and that can be written in the summation as such. Here's where the magic or the headache starts to happen, is when we combine these back into one thing. If we have this in one summation, then we get this really monstrous equation that we just need to take it part by part in order to analyze. The first thing to do is, what do we do with this line integral here, where we're summing over the L and J? Well, here, if we apply Lemma 1, which I will define for you in a couple slides, then we get another crystal symbol out, or Levi symbol out, but this time it's with the AM term because of whatever we integrated through. But then if we have the double symbols here, then we get the double difference Kronecker delta from another lemma. And this helps us sift through the fact that we only need a certain amount of components. And that's why you see when we're summing over JKL, then we go to JKL and M, then it just turns into KLM all the way down to K. Okay, so now we're just knocking out dimensions with these symbols. These are very hectic, and if you want, I'll supply the proof of these lemmas. But to get used to all these things, it's just a mess. Hopefully, and take it in good faith until you play with it yourself. But now we get to these physical interpretations of what we whittled down, where we have del naught dot B naught equals 0. Well, clearly there are no monopoles. But also that we have M equal IA due to just the magnetic definition of the magnetic dipole. So if we plug these things in, we get a nice 0 there. Now we can plug in what the current is. Well, when we distribute the current to the A or the area vector, then we get M. And we see that we get the same thing here. The subscript just reminds us to take the derivatives at the point where M is located. And we get the result we're looking for, albeit after a ton of mess. And here are the lemmas that were used, where you had the closed integral RL dLj is equal to the summation, but also then lemma 2 is what happens when I have two of the Levi symbols. These things are gross. Get used to them where you can, and maybe I'll just include a worksheet for it because I needed a lot of practice myself. But they're fun once you get a hang of it.